Thank you. So I'd like to start by thanking the organizers for putting together such a wonderful meeting. It's a real pleasure to be here and a privilege to give the talk to you. So some of you may have noticed that my title is now more general than what appears on the schedule. This is because I want to tell you about a number of different developments, but all unified under a common theme. Some of those are already have appeared, and some of them are still work in progress. So let me motivate the common theme. Okay, so as you all know, for a decade and a half, the ADS-CFT correspondence had a resounding success in providing invaluable insight into both the dynamics of strongly coupled field theories on the one hand, and into quantum gravity on the other. I think that we have barely seen the tip of the iceberg, and that the correspondence has the most profound lessons yet to teach us. To fully utilize the potential, we still need to understand the correspondence at a deeper level. And as a starting point, we need to further develop the dictionary between the two sides of the correspondence. Now, you might expect that physically important, or in some sense, natural constructs on one side have correspondingly important or natural dual on the other side, although it might be in completely different guise. And one example that I find particularly fascinating is, has to do with the recent developments in the quantum information theory, where, and the intriguing hints that we have about its relation to quantum gravity. So as we heard already yesterday, the sort of fundamental notion of in quantum information theoretic concepts like entanglement is somehow intimately related to geometry. And so it's quite natural to sort of study geometrical or causally well-defined constructs in the bulk. And so, rather than focusing on situations with high degree of symmetry, where we can carry out calculations explicitly, we'll take the sort of converse or complementary approach of insisting on full generality, but use general covariance as the guiding principle for letting us formulate our constructs. Okay, so I'll give you 3 examples of where this has been very useful. The first set is something that you're all very familiar with, what we have just heard about, entanglement entropy, the holographic entanglement entropy, where the important construct is what we are calling entanglement wedge in this upcoming paper. And intertwined with this theme is an object that we have been thinking about in the last few years called the causal wedge. Okay, so that's one set of examples. The second set of examples is what I called strip wedge and rim wedge in this paper that came out just last week. And if I still have time, I'll get to the sort of most speculative part of the talk, which, it's innocuously sounding. I'll tell you about sort of generalizations of Poincare wedge. Okay, so let me start with the familiar holographic entanglement entropy. Okay, so as you all know, the proposal of Ryo and Takayanagi for static situations where you can look at a given instant in time was to say that the entanglement entropy of a certain region was given by the area of a minimal surface at the constant time, which is anchored on the entangling surface and homologous to the region. Now, this has a tremendous success and was great in geometrizing our intuition already about entanglement in these static situations. And we have large body of evidence now for this correspondence. And ultimately culminating in the Lefkowitz-Maldacena argument based on the Euclidean quantum gravity path integral. But we still have to face up to the issue that we live in Lorentzian space-time, time-dependent Lorentzian space-time, where these convenient Euclidean techniques don't apply. But nevertheless, the notion of entanglement is, of course, well defined for arbitrary time dependence. And so that has motivated us to generalize the holographic prescription to arbitrary time-dependent space-time. And here, the guiding principle was precisely to formulate some well-defined quantity that doesn't depend on any coordinates and, is fully general. So you can't rely on, constant time surface because constant time doesn't have any natural geometrical meaning in this time-dependent situation. And you can't construct a minimal surface because you can always decrease the area by, wiggling the surface in the time-like direction. And so we had a couple of natural candidates, but the one that seems to have fit all the data is that, well, the minimal surface at constant time simply becomes extremal surface in the full bulk space-time with the rest of the, conditions the same. Now, you can also equivalently think of this extremal surface as simply one with zero null expansions, as Raphael explained to us very nicely what that means yesterday. So you can think of this as something that generates the light sheets from it. And there's another description that you could also, that's equivalent to this, but I'm not going to go into that. But, so the point is that, okay, so now we have this more general prescription, and now we have to check that it's the correct one, and we don't have the nice Euclidean techniques to prove it. So we have to sort of try to figure out whether it satisfies all the natural physical constraints. And the new element here is that we have time dependence, and so we need to check that it satisfies causality requirement that comes from any local quantum field theory, in particular the dual CFT. And so in particular, the entanglement entropy must satisfy the fact that, well, here, if it's pertaining to some region, really it's an object that's defined for the full domain of dependence, or said differently, it depends on the entangling surface on the boundary of this region, rather than the actual slice. And so if you deform the state somewhere here, the entanglement entropy can't change, because you could have taken, instead of this slice, you could have taken one that went way down in the past, like this. And there's a natural way to sort of split up space-time based on this entangling surface, boundary of this region, into these four regions: the domain of dependence of your slice, the domain of dependence of the complement, and the causal future and causal past of your entangling surface. And the requirement that's given to you from just quantum field theory locality is that the entanglement entropy cannot be influenced by anything that happens in here or in the future, of course. So it can only be influenced by what happens here. And so you need to check that this is indeed somehow captured by the holographic description. So what is the danger? Well, so here, well, first of all, we should ask what is the most natural sort of bulk construct that corresponds to the domain of dependence of your region, and that's what we call the causal wedge. So the causal wedge is, I have sketched it here. Here is the bulk radial direction, and this is the boundary. So you take the set of all causal curves that start and end in this domain of dependence, and that forms for you this causal wedge. And the rim, just as an aside, the rim of the causal wedge which is again defined just purely causally, based on causal constructs, is what we're calling this causal information surface, this psi. And you can specify its area in Planck units, quarter of its area, as what Mukund and I call the causal holographic information. Okay, that was defined in this paper. And in special cases, in pure ADS or BTZ geometry or higher dimensional ADS and round regions, it actually turns out that this causal wedge, well, this causal information surface precisely coincides with the extremal surface that's anchored on the boundary of this region, but in general they differ. So in these special cases, this causal holographic information just coincides with the entanglement entropy, but in general they're different. And it's an important and open question. What is the interpretation of these constructs in the field theory? Which are, I mean, it's an important question because the causal wedge is in some sense the most basic construct, because it only requires you to know the causal structure. You don't even need to know the geometry. So here's a very beautiful natural construct pertaining to a region, but what does it really correspond to in the field theory? Okay, so let me go back to the issue of entanglement entropy. So what does one need for the entanglement entropy to satisfy in order to uphold this boundary causality? And it's that this extremal surface must lie not only outside the causal wedge, so that you can't influence it, but also it must be space-like related to this causal information surface. And we have shown that it has to be, it cannot be inside the causal wedge, but it looks like it's marginally safe or marginally unsafe, because there are special situations where the extremal surface is actually null related to this causal information surface. So here is a space-time which is a collapsing black hole. There's a shell which creates a horizon. So this is ADS with a black hole that's been formed called by the ADS. And I have drawn the causal wedge for a given surface before the shell and after the shell. And the extremal surface actually ends up being null related in this special case to the causal information surface. And so you might imagine that if you deform this extremal surface just a little bit, then you would already be in this danger zone. The danger is that you might get the extremal surface that mocks up entanglement entropy to be influenceable by something that happens in this causal domain. Another danger is in the double-sided context, where you have two-sided, say, a black hole geometry. So this is the eternal Schwarzschild ADS geometry, where you can think of one CFT living here and a completely separate, decoupled CFT, but entangled with this one living here. And it's easy to show that for this static situation, there is no extremal surface that can be anchored on this side that could actually reach to be in causal contact with the other side. But at the same time, if the black hole is dynamical, because the event horizon is defined teleologically, it's easy to find examples where the extremal surface goes inside the horizon. In fact, we have seen one just on the previous slide. Here, this comes inside the horizon. And so you might imagine that if you take this eternal static black hole and deform it, again by throwing in some shell, that you can get a situation where the extremal surface actually gets, sort of say, into one of these regions. So now you have causally split the space-time, and you have many of these causally defined regions. So you might imagine that the extremal surface penetrates here, which would be problematic, because then you could influence a quantity that you measure on this side by something that you do from the other CFT. And that certainly would be contradictory. Okay, so that's the second danger. And so, you need to satisfy, you need to make sure that when you define this extremal surface as the holographic entanglement entropy, that it doesn't lead to these inconsistencies. That's what we have done in this upcoming paper. So one can show that indeed the extremal surface is space-like related to the causal information surface. And the proof is actually not so difficult. You can show it in full generality, and it's basically based on the Ricciardo-Harris equation. But in formulating the proof, it led us very naturally to this notion of entanglement wedge. So what is the entanglement wedge? So just as the boundary spacetime has this natural separation into 4 regions, so does the bulk spacetime. So the bulk spacetime, here again I have drawn ADS, there is my region, here is an extremal surface that's anchored on the boundary of that region. And now you can define 4 spacetime regions, just causally. So there's 2 regions which are consist of time-like separated points from my extremal surface, the future of it and the past of it, and 2 regions which are consist of space-like separated points, the ones that are connected to my original region and the ones that are connected to its complement. Okay, so this former one is what we're calling the entanglement wedge. The entanglement wedge is the set of space-like separated points from the extremal surface that's connected to the region. And it's easy to show that this entanglement wedge, well, it's the boundary, its restriction to the boundary of ADS coincides precisely with the domain of dependence of the region, this guy, but as would the causal wedge, but this is larger than the causal wedge. The causal information surface for this region would lie somewhere sort of closer to that region, and the causal wedge would lie entirely inside, or at best in pure ADS coincide with this entanglement wedge. And the important point is that the boundary of this causal set, causally defined set, is generated by null geodesics, which start from this extremal surface. Now, there was this nice question, I guess, posed by Mark and friends some years ago, but in this work, what is the, and simultaneously in the work by Busso and friends, what is the dual of the density matrix? Suppose you know the reduced density matrix for a given region. Is there a natural region in the bulk spacetime that you can somehow recover from the reduced density matrix? And Busso and friends suggested, based on light sheet arguments, that the natural dual should be the causal wedge, whereas this group, and later Aaron Wall, suggested that it should be given by, well, what ends up precisely coinciding with the entanglement wedge, although they didn't quite formulate it the way that I have described it, but it boils down to the same thing. And we conjecture likewise that that is the correct way of thinking about it, that the entanglement wedge is the most natural dual of this reduced density matrix. But that leads to a nice, well, or curious effect or consequence, which is that the entanglement wedge can see regions which are causally disconnected from the boundary. So if you take, again, one of these eternal black hole geometries, the double-sided one, but deform it a little bit, so that, well, the Penrose diagram will widen in general, and so the horizons, the event horizons for the 2 sides don't, well, leave some, what we call a shadow region behind, some finite region that's causally disconnected from both boundaries. So in such a situation, let's suppose that our original region A wasn't just some finite region, but the entire Cauchy slice of one boundary or the other boundary. And in that case, we're saying that the extremal surface must lie somewhere in this shadow region. So if this was the static Schwarzschild ADS geometry, the extremal surface would have been the bifurcation surface of the black hole. This whole region would have shrunk to just a point on this diagram, and that's where the extremal surface would be. But in general, if you have completely, dynamical situation with these 2 sides, you still have the result that the extremal surface lies inside the shadow region, and that means that entanglement wedge actually goes past the horizon. And so our conjecture is saying that you can actually see more than just what's outside the black hole. Okay, so let me now quickly, before moving on to the second set of topics, tell you a curious, curious upshot of the result of the causal wedge, which is, so far it had played sort of a side role, but there's a nice effect that's a consequence of properties of causal wedge that pertains even to entanglement entropy, and that's the following. If you have a black hole in your geometry and you take sufficiently large region, then you can show very easily that the causal wedge must have a hole. It can't contain points inside the black hole, but at the same time it contains everything sort of around like this. And that means that there cannot be an extremal surface that's homologous to this region that's in single piece, because then it would have to lie inside the causal wedge, and we have said that that can't happen. And so that implies that the extremal surface must come in two pieces, one sort of that's homologous to the complement region and one that's around the black hole. And that means, that leads to this nice relation that the entanglement difference between the entanglement entropy of your region and its complement is given precisely just by the black hole entropy. And so this saturates the Araki-Leap inequality and leads to what we call the entanglement plateaus. Once you take a region that's sufficiently big, this difference is always just precisely this black hole entropy. And that's a very robust result. You can confirm it for static short-shell black hole, but this argument based on the causal wedge holds for arbitrary time dependence and so forth. Okay, so that's one nice result. Okay, so let me now quickly go to this second topic. So you heard from Jan de Boer yesterday about this residual entropy as a quantity characterizing a collective ignorance of a family of observers. And you can think of the family of observers as ones in the bulk that don't have, that cannot see inside a certain space-time region, some hole here, or you can think of it also as a collective ignorance of boundary observers that are restricted to live within a certain time strip. And these authors sort of suggested a formula which they later renamed to differential entropy in terms of entanglement entropies of sort of intersecting intervals, as Jan told us yesterday. But that prescription is severely limited. It works only in 3 dimensions, only for pure ADS, only when you have time flip symmetry, and on top of all that, only when your regions, the bulk hole here or the time strip, is not too wiggly. Okay, so, and the upshot is, in general, this differential entropy does not capture what you wanted initially, this residual entropy characterizing the collective ignorance. Okay, so you might ask, is there a more robust notion of the entanglement of the residual entropy? And the answer is yes. And again, you can define it by a causal construction. So the problem with the why you need sufficiently smooth case is that if you take this set of Rindler observers that don't see inside the hole, it turns out that, so they wanted to take null geodesics that sort of go perpendicular to this hole, but sometimes these geodesics intersect. And once they do, the remainder of them is time-like related to their starting point, and so it's not causally disconnected from this hole. So the natural prescription now is to cut off these generators after their intersection and define what I called 2 quantities, a rim wedge or a strip wedge, depending on which observers you're taking, whether the boundary ones, or the bulk ones or the boundary ones. So the proposal is that the rim wedge is given by the sort of space-like separating points from the bulk hole. That's in a sense analogous to this entanglement wedge. It's a generalization of that for arbitrary shaped surfaces. And strip wedge is something that's just like a generalization of the causal wedge, now pertaining to this full time strip. Now, the curious effect is that if you have sufficiently tame situation where these null generators don't intersect each other, the two notions coincide, but in general, they differ. They differ because these generators hit a caustic, and the nature of the caustics is different depending on what is your starting point. And that leads to an important effect that you can't sort of reverse construct. Suppose you start with this bulk hole, you construct the time strip, and now you want to go back to construct some bulk hole from this kinky time strip. Well, you can't do it. You can't recover the entire curve. You only recover some parts of it. Similarly, if you start here, you recover back only some parts of this time strip, and you miss other ones. Okay, I'm almost ended. So this leads to an interesting puzzle that if you now want to specify what is the residual entropy, it's actually not, this irreversibility leads to the conclusion that somehow the residual entropy of the bulk cannot be described in general by local observers on the boundary, and conversely, that somehow this collective uncertainty is a notion that is much more globally defined than just taking a set of observers. So since I'm out of time, I'll skip my third topic and just put up the summary. The main lesson of all this was that a general covariance is a very powerful sort of guiding principle. And there are various of these sets that you can define just based on, causality, causal set, and they lead to important consequences that you can ascertain without, having to deal with explicitly calculating some surfaces in a given complicated geometry. You can just use GR to make statements about such surfaces. The other conclusion is that the HRT proposal, this covariant holographic entanglement entropy, is fully consistent with causality, and this entanglement wedge is the most natural dual of the density matrix. Okay, so let me just stop.
Veronika, so I believe that your proof of the causality of the extremal surface that used Einstein equation.
Mm-hmm. It used Residual's equation. So if you have some positive energy in the bulk, your geodesics, null geodesics, once they are not expanding, they cannot start expanding. They will have to converge, and that leads to the problem like. Well, actually, you can even see it here. These generators sort of will caustic and not reach the boundary, and the proof sort of rests on that.
So I was just wondering whether by turning the argument around, if you demand causality, then you can sort of derive Einstein equation the way this first law arguments are turned around to.
That's a very interesting question. So this is sort of similar along the lines of sort of what Mark was talking about yesterday. You won't be able to derive all of the Einstein's equations, but you certainly might be able to, derive some parts of it.
The elements that are involved in the Residual equation and the caustics.
But so maybe we can talk about that later.
Question? Actually, I thought you had one. You've changed your mind? Yeah, okay. Hello? Yeah, so it would certainly be great if we could reconstruct all the way to the entropy wedge. It's not immediately clear that you can do that using the reconstruction methods that people know about, involving, space-like Green's functions and things. I mean, it looks like you'd have some boundary condition on the singularity there if you were going to do that. So do you have any ideas about this or comments?
Well, so what is certainly true is that you have a set of extremal surfaces that that are anchored, sort of, if they're anchored within this domain of dependence of the original region, they will keep penetrating sort of up to this surface. Now, you might imagine that these codimension 2 extremal surfaces have a given area, and if you take a difference between nearby ones, okay, then you can sort of start reconstructing the metric by sort of looking, you can sort of bootstrap from the boundary. You can start with tiny surface here, figure out how much it deviates from pure ADS, and sort of keep going into the bulk until you reach this surface. So by this differencing, you might be able to recover the parts of the metric that the extremal surface know about.
You think that could work even in the case where you have the wormhole with where you take your entangling surface to be the whole right side in the CFT, and then the entangling surface is really in this causal shadow, or sorry, the extremal surface is really in the causal shadow.
So if you have a planar black hole geometry, where you can take these regions arbitrarily large, then I think the answer is yes, because they can penetrate all the way up to it. If you take this global geometry, global black hole, then there's a jump between sort of the largest surface you can sort of fit here and the full Cauchy slice. But
yeah, so that's what I'm worried about.
But for the planar one, you could actually.
Okay, but for the spherical one, it's unclear then.
For spherical one, there's a gap, but you can still go inside the black hole.
Somewhat, yeah.
You can still go inside the black hole somewhat, but.
Question? So it probably just went by quickly for me in the talk, but with these last wedges that you talked about, the strip wedge and the rim wedge.
Okay, this is a good
so
picture for
did you have, were you suggesting some natural field theory quantity that would capture the same information as these wedges? So the entanglement wedge seems to naturally correspond to a density matrix for a particular subset. Do you think there's some natural subset of the information that you could describe in the field theory that corresponds to those, or one of these constructions?
So for this strip wedge, that was constructed based on a collective ignorance of boundary observers that are allowed to only last within this time strip. So I'm suggesting that this strip wedge is the quantity that naturally encompasses that residual entropy for these boundary observers. Okay. Now, what is the actual number that you would extract out of this is a much harder question. You might naturally think that this analog of the causal holographic information, the area of this rim of the strip wedge, is the most natural quantity that should have been identified with the residual entropy. But that leads to a puzzle, because you could have different boundary strips, time strips, that would lead to the same surface here. The point is that you would have, if you start, for example, from this green curve, you would have these null geodesics all meeting up at this point, rather than cross-linking with each other, but nevertheless, that would still lead to the same area. And therefore, there are different time strips that would lead to the same, what you would have conjectured to be the same residual entropy, and so that's puzzling. Now, for the other side, you start with some bulk hole, so that's already a set of bulk observers. There you might say that the residual entropy is naturally just given by its area, but then you have the converse puzzle that if all you have an access to is the boundary set of observers, okay, the time strip that you see is not unique for a given bulk hole. So different area holes have different bulk surface. But the wedges are unique. So the wedges are the thing that should capture both residual entropies.
Okay, we're almost out of time. I don't know if it's allowed, but I have a question, very brief. It occurred to me during the talk, and I apologize if this is mentioned in all your collective papers on this subject, but I remember years ago, one of the approaches to quantum gravity people had was sort of doing dynamics on causal sets. I think people like Faye Dowker and people like that were working on that. Is there any relation? It just sort of sounds like a lot of the words and pictures are
Well, I use the
related.
statement, the phrase causal set, simply to describe a set that's defined causally.
Sure, but
Okay,
I wonder if the approaches might have something to teach each other or not.
So in Dowker and company's approach, the main concept was that if you have quantum gravity and you assume that the thing that's, even though space-time itself is emergent, that somehow the causal structure is fundamental enough that it remains even in quantum gravity, fully quantum gravity. I'm not saying any such thing here. I think space-time is fundamentally emergent from the CFT degrees of freedom, and we don't really know how it happens. And I'm not claiming that the causal structure itself, which will be something that is already is going to be there without emerging.
I just wondered whether some of the language might be useful to each other.
But certainly, in terms of using GR for these causal structures is important in both approaches.
Okay, let's thank the speaker one last time and go to break.